Hi, welcome to videos on feedback amplifiers. So in this feedback amplifier videos, we'll see the theory and analysis of different feedback amplifiers. In this particular video, we'll see the advantages of negative feedback in amplifiers. So the reference for this particular video is taken from Microelectronic Circuits by Cedra Smith. This is how an amplifier with negative feedback will look like. So this is an amplifier, and we are taking a portion of the output voltage through a feedback factor beta onto the input, since it is negatively fed to the input side. So that's why this is called as negative feedback. We have a source, we have a load, and these are amplifiers, and this beta is a feedback factor. Since it is negative, we have a we call this as negative feedback amplifiers. So let us see what are the advantages of negative feedback. So first one is, of course, negative feedback is also called as degenerative feedback. So first and foremost advantage is it will actually desensitize the gain. So the meaning of desensitization of the gain is, assume that you have an amplifier with a gain A. Assume that this amplifier can be a differential amplifier, it can be a common source amplifier, it can be any amplifier, because we know that every amplifier gain depends on the circuit components. Like in this particular case, it depends on RD, it depends on what is the transconductance of this particular transistor. Suppose if any of the parameters, circuit parameter like RD, GM, which in turn depends on the W by L, if any of these parameters changes due to some physical phenomenon, maybe the RD may change because of the temperature, because of fabrication. Suppose if the dimension of these slightly changes because of some reason or the other, so we know that the gain will go to directly affect. So it is very sensitive to the changes in the parameter, circuit parameter, due to the changes. So upon doing that negative feedback, the gain of the amplifier will not be that much sensitive. So what it says is, make the value of the gain less sensitive to variations in the values of the circuit components, such as of course such might have been caused due to the changes in temperature. So as we discussed here, if RD changes, this A is changing very rapidly, so it is very sensitive to the amplifier gain is very sensitive to this. So by doing this negative feedback configuration, you are making sure that the overall gain of this amplifier is not so sensitive as it was without feedback. So without feedback it was very sensitive. With feedback, the sensitivity of the amplifier gain will reduce. So that's what is the meaning of desensitization. We will prove that in the coming examples. Upon doing negative feedback, it will actually desensitize the amplifier gain. Next is one of the major advantages, extend the bandwidth of the amplifier. So assume that this solid line has got, assume that this is the frequency response of an operational amplifier. Assume that AM is the gain of an amplifier without feedback. You can see AM is the gain here, DC gain, and you can see there is a 3 dB bandwidth. So 3 dB bandwidth is at omega h. So this is having a limited bandwidth because of high gain. And when you provide the negative feedback, you can see the gain is reducing. More than that, what we are looking at is extended bandwidth. So bandwidth of the amplifier which was there at omega h will go to omega hf. So this is omega hf corresponds to the bandwidth after feedback. So you can see the bandwidth which was there at omega h will go to omega hf. So this is what we call it as extension of the bandwidth of an amplifier due to negative feedback. So third most important advantage is reduce the effect of noise. So we know that all the amplifiers are used to amplify the signal, but unfortunately you may have along with the signal you may have the noise coming in, and it is also possible that the amplifier itself will introduce the noise. So this noise can be either from the components that are there within the amplifier, or it can be an external one. So that's what it is meaning. Minimize the contribution to the output of unwanted electrical signals generated either by the circuit component themselves or by extraneous interference. So you can have a signal in the form of external as a noise, and the noise can be generated within that. Using actually negative feedback, whatever noise that you are having being generated in the amplifier or which is coming from an external source will be actually reduced when you actually do a negative feedback. So we're going to again prove this also in an example. How does a negative feedback will reduce the noise level, or it will increase the signal level at the output voltage. Next, one more important parameter is reduce the nonlinear distortion. So what is this nonlinear distortion is? Because we know that all these amplifiers will effectively use a nonlinear device in the form of MOSFET. It can be BJT, it can be MOSFET. So we know that both BJT and MOSFETs are nonlinear devices, meaning as the input voltage changes, the gain of the amplifier will also keep changing. So what we want to do is the gain of the amplifier should be almost independent of the amplitude of the input signal. So using negative feedback, it actually reduces the nonlinearity distortion. So over a range of input voltage, the gain is almost constant. So that's what is the meaning of reducing the nonlinear distortion of an amplifier. That will certainly happen because of negative feedback. So you can see this what make the output voltage proportional to the input. In other words, make the gain constant. It should be independent of the signal level. So if the signal level is 10 millivolt, the gain should be X. Even if it is 100 millivolt, it should be again X. So it should not reduce as the input amplitude increases. So we want to ensure that it is independent of the signal level. And again, one more most important advantage of negative feedback in the amplifiers is we know that all the amplifiers will have some input impedance and output impedance. Ideally, we say that the input impedance is infinite and the output impedance is like 0. But they're going to have typically very high impedance and very low output resistance. Actually, by doing the negative feedback, whatever resistance you have without feedback will be certainly boosted after you do the feedback. So this Ri will be more in case of if you do a negative feedback. Again, this Rout will be lesser than whatever the specific value of an amplifier before feedback. So this negative feedback will increase this Ri and R0 after providing the feedback. So that's what it says, rises or lowers the input and output resistance by selecting appropriate feedback topology. It rises the input but it lowers the output resistance by using appropriate feedback topology. These topologies we'll be discussing in the coming classes, coming videos. So these are the 5 different advantages. So one is the increasing the resistance, input resistance, reducing the output resistance, and reducing the non-linear distortion. That is, over a wide range of input voltage, the gain should be constant. And then the effect of noise. So whatever that noise that is there coming externally and coming within that, we need to have a lesser impact of that on the output voltage, and extending the bandwidth of an amplifier, and most importantly, making the gain desensitized with the changes in the parameters, circuit parameters, which may usually happen due to gain change in the temperature. So these are the 5 major advantages of going for a negative feedback in an amplifier. So let us take one example so that we can understand how does this is going to make desensitize the gain and all those things. Okay, this is a source, this is a load, and we have an amplifier. There is a feedback, and we know that A happens to be the open loop gain without providing any feedback. Once you provide a feedback of beta, so we can write the expression for the closed loop gain of this amplifier with this negative feedback as A by 1 plus A beta. This is what we know from control system. This is like a closed loop transfer function of a system having A as a forward path gain and beta as a feedback path gain. So it is A by 1 plus A beta. Let us see how do we understand this desensitization. So we know that this is the expression for the closed loop gain, you differentiate this AF, that's what is the differentiation of AF is given by this. So you have dA by 1 plus A beta whole square. Now this entire equation you divide by AF. Now dAF by AF, and then this entire thing divide by, of course, divide by AF or multiplied by 1 over AF. So now we are dividing this expression by AF on both sides, that is on the left hand side as well as on the right hand side. You end up with this expression. Now you keep substituting what is AF here. So AF, you know that it is A by 1 plus A beta, so that's what we did here. So we have replaced AF by this A by 1 plus A beta, it goes there. So you end up with an expression which is, one second, okay, the final expression will be dAF by AF happens to be 1 over 1 plus A beta dA by A. So what does this actual meaning of dAF by AF is equal to 1 over A plus beta is? Okay, this is what is written here. If dA by A, so if this is the change in the gain of an amplifier without feedback, this is dA by A. So this shows that the percentage change in AF due to circuit parameters, that is, this is the percentage change in AF due to circuit parameter with respect to percentage change in A, that is without feedback. If you can see here, if I just read out this shows that the percentage change in AF is smaller than the percentage change in A by a factor equal to the amount of feedback. So this entire quantity 1 plus A beta is called as amount of feedback. So we will going to always have, this is the percentage change in the gain of an amplifier with feedback. This is a percentage change of an amplifier without feedback. If you can see, change in the amplifier gain with feedback is far lesser than the change in the gain of the amplifier without feedback by an amount equal to 1 plus A beta. So this is always lesser compared to this. So if it is X percent, so this will be Y percent. Always Y percent is lesser than X percent by this much amount. So we will take up an example and then try to find out how does this will affect. So now we consider an amplifier with a nominal gain of 1000 volt per volt exhibits 10% change in its values when the temperature changes from 25 degree to 75 degree. Meaning that this is 1000, so this may go to 100 and 1000 and 1100, so 1100. So gain may become 1100 because it is a 10% change, and now it is required to constrain the change to only 0.1%. Now you can see it's almost 10%. I want to reduce this gain to only 1.1% change. You can see there is a huge change in the gain, so that should be restricted to only 0.1%. So that can be accomplished using a negative feedback. Now, suppose when you are doing a negative feedback, it is very sure that a gain will going to reduce. Now they are asking, if you are reducing the sensitivity from 10% to 0.1%, what is the largest closed loop gain that you can able to get it? Because whatever reduction in the sensitivity you are getting is at the cost of reduction of the gain. Now they are asking for what is the maximum closed loop gain that you want to have. Next is, if there are 3 such feedback amplifier placed in cascade, what is the overall gain? And they are asking for what is the gain stability. So for this, you know that this is the specification given. So this is 1000, dA by A is given as 10%, that is percentage change in the amplifier gain without feedback is 0.1. Percentage gain in the amplifier with feedback has to be 0.1%, that is 0.01. Using this expression, I can write it as 1 plus A beta will become 100. If 1 plus A beta is 100, I can actually find out what is the AF. So I know what is A, I know what is 1 plus A beta, it is 100. So maximum gain we're going to get is only 100. So using this 100, from this 10,000 it has, from this 1000 it has reduced to only 10 volt per volt, but the sensitivity has reduced from 10% to 0.1%. If you cascade them 3 in series, you're going to get a gain of again 1000, but you can see the cascaded gain is 1000 you're getting. Now the gain stability is reduced to reduced from 10% to hardly 0.3%. So this is how you can get that right.